All right, you always want to make sure that you are looking at the correct lesson. And so this is Algebra 1, and all the Algebra 1 title screens will be red, try to help you out there. And this is lesson 1.1, so the first lesson of a new school year, and it's titled Sets of Numbers. So lesson 1.1, sets of numbers. And what you'll want to do is this. We would have covered the beginning of this lesson in class this morning. And so what you'll want to do is fast forward, find the place where we left off. And don't forget, you want to also take good notes. So even though you're at home and hopefully in a little bit more relaxing atmosphere, you're still going to need to take notes, and that will help you out. All right, so this is lesson 1.1, and it is sets of numbers. So lesson 1.1, sets of numbers. And we're going to start off with some terminology. So terms. When you think about a set, you have to think of a group or a collection of objects. So that's number one. What is a set? And I'm going to write the word set in red. What is a set? It's simply a group or collection, of objects. A group or collection of objects. And you're going to use sets to organize things. You're going to use sets to classify things. When I think about sets, in modern day usage, I think about file system. So for example, here is my computer's document section, right? And so, here we are, really, we're in libraries, and I can then further go in. So I've got the set of documents, and I can then get into the set of documents. Let's see if this is going to work for me. Okay. So I can get into the set of documents. And now there are all of some subsets. We'll talk about that in a little bit. And I've got all these files, and let me go down here to Smart Notebook, and that's the program I'm using right now to teach this lesson. And inside Smart Notebook, I now have some other files. And so these are all sets and subsets of a greater set. And our class is Algebra 1, and that's right up here, top left. And I'm going to go to the Algebra 1 folder, and inside that we have numbers of sets. The set of the folder 2012-13, 2013-14, 14-15, etc. And then there are just some random files that are in there. And of course I can go to 14-15, that's this year's file, and I can see now the chapter 1 lesson is there, a couple seating charts, and the heading. And so sets, and again, I'll walk it backwards. So those items are a group or collection of items within Algebra 14-15, which was within the Algebra folder, right? Let's go back. All right, we're getting stuck there. Which was part of Smart Notebook, which was part of Documents, which was part of Libraries. Just some concepts of sets. So it's a group or collection of objects. And what we're going to do in algebra is we're going to deal with sets of numbers. And our numbers are going to be classified in a system of sets. That's where we're heading, and that's what we're after. All right, within each set are the objects. And so each object, number 2, each object is called n. Each object is called n, and I'm going to go to green here, element. Each object is called an element. And again, sometimes we'll call them objects, sometimes we'll call them elements. Technically, the word is element. All right, so each object is called an element. All right, sets. And I'm going to show you some example sets here in a minute. We're just trying to lay a little bit of groundwork right now. Number 3, a set with no elements. A set with, and I'm going to write in red, no elements. Kind of a boring set. There's nothing in it. A set with no elements is called the empty set. Gee, that's real profound, isn't it? It's called the empty set, or one other name, the null set. Empty set or null set. And they're one and the same. They mean the same thing. You know, if you're thinking about file folders, so let's suppose I had a file folder for this class, Algebra 1, 2014, 2015, and I had yet to put anything in the file folder. For example, let's suppose I had a homework file folder. Have we done any homework yet? No. So I open up the file, there's nothing in it, right? There are no elements inside the folder. Then it would be the empty set or the null set. Now there are a couple symbols here. So the symbols for the empty set is a piece of cake. See, sets always come encased in braces. So you always have braces, a left brace and a right brace, and in between the braces are all the elements that are listed. Well, if it's the empty set, you've got nothing in there, right? So that would be the symbol for the empty set. The null set is a familiar symbol. I always like to talk about Ghostbusters, and you know, you'd have that circle around the ghost and the line through it, and really we use it as not. You know, you can't go through that. Well, that's the symbol for null set, and again, that means there's nothing inside the set. Number 4, what else? Number 4, sets can be, and I'm going to go to green here, finite or infinite. Sets can be finite or infinite. Sets can be finite or infinite. Now remember, we're talking here about numbers because this is algebra. And so our sets are going to be sets of numbers. So you can have a finite set. There's only certain numbers inside that set. Or you can have an infinite set. It just goes on forever. You know, the counting numbers, 1, 2, 3, 4, 5, and you can count forever, correct? That would be an infinite set. So there are infinite sets and there are finite sets, and you'll have both. All right, so just some terminology. Capital B, using sets. Using sets. Capital B, using sets. And for sake of illustration here, let's have 2 example sets. So let's go set G. Capital G is just a designation so we know what set we're talking about. A minute ago when I showed you the files, each main folder had a name. So G is the name of this set. Right, as I told you, when we're going to list the objects, we always use braces. So first we have to have a brace, and then I'm going to put in there a -3, comma, -1, comma, 1, comma, 3, comma, 5. So -3, -1, 1, 3, 5. So that's what? 1, 2, 3, 4, 5 elements in there. Okay, so there are 5 elements in the set. Is that set infinite or is it finite? Well, hopefully you said it's finite, right? There's 5 elements. Is there an infinite number of elements in there? No, it's only 5. That is a finite set. And we're going to go here, I'm going to use black for set K. And usually, again, we use capital letters to denote a set, not lowercase. We need a brace because we're going to list the members. So we're going to put in this one 0, 1, 2, 7, and 9. 0, 1, 2, 7, and 9, and then a brace to the right as we close the set. So 1, 2, 3, 4, again, 5 elements. Now, why 5? I don't know. Just what I picked for my example. All right, so using sets. Number 1. So let me show you some symbols and ways we can use these. We're going to say this, -3, and then I'm going to take my green here, and I'm going to give a symbol. It's going to kind of look like an E, but it looks something like that. It's kind of a curved E. All right, and then I'm going to take my blue, and after it, I'm going to put capital G. All right, so what does this mean? If I were to say this in words, so in words, and I'm going to use my imply symbol. Those of you that are new to my teaching, I use that symbol all the time. It just means implies. So words implies, and this is how we would say it. -3, I'm going to go to green here. -3 is an element of, and then I'll finish back in blue, set G. And that's true, right? If you look at set G, -3 is an element of set G. We could have said -1 is an element of set G, 1 is a negative set G, etc., etc., etc. All right? Is an element of. Let's come underneath this little a. How about something like this? Is this a true statement? 5 is an element of set K. Is that true? Yes or no? 5 is an element of set K, and you would say, well, no, 5's not in K. It is in G, but it's not in K. All right, remember how the line through the circle was the null set to negate it, to say not, and we do the same thing here. We'll put a line through R is a member of or is an element of symbol. So now you would read this 5 is not an element of set K, and that would be true, right? 5 is not an element of set K. So this is not an element of. Is not an element of. 5 is not an element of set K. All right, elements. You just have to remember, whenever you're talking about the members of a set, you've got to list the members within the braces, and that is important. Braces are used. All right, I only have an A, I don't have a B. The English police will be after me, but oh well, that's just the way it goes. Let me go ahead and catch my sets here so I can use them in a minute. So let's continue on here. Okay, so number 2, let's talk about some operations. So using sets. So we can use sets to identify members of the sets, elements that are in sets and such like that. We're going to also do some operations or show how sets relate to each other. We're going to show how sets relate to each other. And the first one is union. Union. The symbol for union is simply a U. It looks like a U. We don't put any line down, but it looks like a U. That's the symbol for unit. Okay? Union. I'm sorry, not unit. So the symbol for union. There's a lot of different ways we can define this, but this is a simplistic concept, so don't get caught up in the definition, but this is simply how it goes. A set of elements that appear, the set of elements that appear, and I'm going to go to red here, the set of elements that appear in any of the sets. In any of the sets. Now, I'm not a big fan of that definition. Okay, so another way to define it would be all the elements of the first set plus all the elements of the second set. You just don't repeat any of the elements. Okay, that's in normal language. All the elements of, let's take our example here, set G and set K. All right, so what if we did this? Set G union set K. And what we're going to do is we're going to list all the members. Okay, so if I wanted to, I could right now list the -3, -1, 1, 3, 5 of set G. But I like to do things in order, and I like to list them in order. So I'm going to do the -3 of set G, -1 of set G. By the way, they don't have to be in color. I'm just using the color to illustrate. We got the 0 now of set K, right? We're putting the two sets together. This next one I could do either blue or black. But look, we don't list 1 twice. 1 is 1. It's the same thing. And you wouldn't list it twice. We only put a 1 in there one time. All right, we got the 2 of set K. We got the 3 and the 5 of set G. And the 7 and the 9 of set K. And that's the union of the two sets, right? You are putting the two sets together. Union. It's a simplistic concept. You're putting the two together. Just remember, don't repeat any elements. Don't repeat any elements, okay? It's the idea of union. Another operation, we'll do this one in green, is intersection. Intersection. And the symbol for intersection is the upside down U. Okay, that's the symbol for intersection. So again, don't get caught up in the definitions, but intersection, the set of all elements, the set of all elements, and then I'm going to finish in green here, common to all sets, common to all the sets, common to all the sets. Here's what this means in just regular terms. It's simply the members that belong to both sets. So when you're looking at intersection, you're looking at two sets, and you're saying which members are in both the sets. That's intersection. Where do they intersect? You know, when two lines intersect, they intersect at a point, don't they? Well, what is that point? That's a point that's shared by the black line. It's also a point shared by the blue line. They intersect. Well, that's the example here with these sets. The only thing is there can be more than one intersection when you're talking about sets. So we'll take our intersect symbol and again set K. So we're going to intersect set G and set K. We always use braces. And now you get to look at set G and look at set K and say what elements they have in common. And there's only one in this instance, and it's the number 1. Again, they could have a whole bunch of elements in common. They could have no elements in common, at which point the answer would be the empty set or null set, right? If they have nothing in common, no common elements, it would be the empty set or the null set. In this situation, we would call it, in that situation, be called the empty set or null set. Okay, so in this one, we had the common element of 1. Number 4. Number 4. Question. Now, we learned last year in pre-algebra some operations and some properties. Okay, so we learned the commutative property, the associative property, the identity property, inverse property, distributive property, etc. Okay, so I want to ask you this: are the operations of, and I'm going to go to red, union, and now green, intersection, are the operations of union and intersection? So it's really two questions, all right? First off is the operation of union. Second is the operation of intersection. So are the operations of union and intersection commutative? Commutative. Okay, do you remember what commutative was? What was the key word in commutative? What doesn't matter as long as everything's being added or multiplied? All right, hopefully you're thinking of the word order, right? Commutative property says the order doesn't matter. Okay, so here's what we're asking. Is G union K, will it equal K union G? Can we switch the order, and is it true? So putting the two sets together, does it matter if set G is listed first and then set K, or K's first and then set G? Does it matter? No, it doesn't matter. Is it commutative? Is union commutative? Yes. And then the same question would be with intersection. How about intersection? If you're intersecting two sets, does it matter if you say G intersect K, or if you say K intersect G? Does the order matter? And the answer is no, it doesn't matter. Is intersection commutative? And the answer is yes. Both are commutative. All right, number 5. Number 5. Let me see if I still have my sets. I do. Okay, don't worry about green. That can be blue. I thought it was. And number 5. All right, Venn diagrams. Venn diagrams. All right. A Venn diagram is a picture to represent sets. A picture to represent sets. So I'm going to show you union and intersection with a Venn diagram for our two example sets. So first off, let's go G union K. So I'm going to show you the Venn diagram. All right, Venn diagrams start with usually a rectangle. And the rectangle represents all the possibilities. So in this case, it'd be all the numbers that there are. Now, we don't have to list all the numbers. It just represents that. And then usually we'll use circles. You can use rectangles inside or triangles or something, but normally it's circles. So I'm going to make a circle here. And inside the circle, I'm going to put the capital G. Now, the capital G is not an element. It's simply the label. This is set G. And as you can see, I need to now list the numbers in the set. So do this the way I do. I'm going to start here with -3, 1, and I'm going to put 1 over here to the right. Now make sure your 1's over there to the right. It's got to be there. That's important. All right, and I'm going to come down here and put the 3 and the 5. Okay, I listed all the elements of set G, right? Now I'm going to take set K and have to put that in there. Now I have to do something because of the elements of the set. I'm going to catch that 1 with the circle of K, because isn't the element of 1 also in set K? Now if there would be more than 1, I'd have to catch all the numbers that are in both by the overlapped part. Okay, now what else is in K? A 0. Do I list 1 again? No. 1's already in K. The 2, the 7, and the 9. All right. Now, that's a Venn diagram, but we haven't yet shown the union. And the way you show the union is to shade the solution or the union. So what numbers are the union? Everything in G and K, and so we shade G and K. And if you look now, you've got the numbers like we did earlier, -3, -1, and I see I didn't get a negative there, did I? -3, -1, 1, 3, 5, 0. 2, 7, 9 is the union of those two. Now let's go ahead and do intersection. So again, intersection is like this, and it's going to start out the same way. We're going to start the exact same way. Again, I start with G. Now I'm already looking, and I already noticed they overlap at 1, so I want that 1 over there again. So -3, -1, 3, 5. Take my K, overlap the part where they intersect. Also have a 0, the 2, the 7, the 9. And what would I shade this time for intersection? Only the solution, right? And so I would shade the intersected part or the 1. So those are Venn diagrams of union and intersection. A Venn diagram of union and intersection. And remember, for union and intersection, the shading is the solution. The shading is the solution. All right, a couple more concepts here. Number 6. Number 6 is the concept of subsets. Subset. Earlier, when I talked about the folders, I used the word subset. What a subset means is it's part of a larger set. Part of a larger set. All right, so the symbol for subset, we take that U again, we put it sideways. And then we're going to put a line underneath, and that's the symbol for subset. And so what is subset? It's basically this. If every member of the first set, is also a member If every member of the first set is also a member of the second set, then, this is an if-then situation like geometry, then the first set is a subset of the second set. Then the first set is a subset of the second set. If every member of the first set is also a member of the second set, then the first set is a subset of the second set. All right, for way of example here, let's list a couple sets. Okay, so let's go capital A equals, we'll go brace, let's go 1, 7, 10, and then close it with a brace. All right, so set A has 1, 7, 10 in it. By the way, I should have said this way earlier. Remember, you can pause this, right? You can rewind. If I'm going too fast for you, pause. If you need to stop and think about it a little bit more, pause. If you need to rewind, rewind. You've got that capability, right? You've got a video. All right, capital B, set B has the elements 2, 7, 10, brace. So capital B equals brace, 2, 7, 10, brace. Let's go one more, set C equals brace. Let's put in there 1, 2, 7, 10, 12. 1, 2, 7, 10, 12. 1, 2, 7, 10, 12. All right, so here's the first question. Is this true? Is A subset of set C? In other words, are all the elements of A also in C? Is the 1 of A in C? Yes. Is the 7 of A in C? Yes. Is the 10 of A in C? Yes. All the members of A are in C. So yes, it is a subset. By the way, if you look also, you'll notice that B is also a subset of set C. Is the 2 of B in C? Is the 7 of B in C? Is the 10 of B in C? The answer is yes. B is a subset of C. Is A a subset of B? And the answer is no, right? So if we did this, is A a subset of B? Is the 1 of A and B? No, all right, already we're gone, right? So how would you show that? Use the negation, right? A is not a subset of B because all the members of A are not in B. So I'm going to ask this question. Is subset commutative? Is subset commutative? All right, so let's just look at this. We already said that A is a subset of C, right? We've already said that. So can we then change the order? Is C a subset of A? Is C a subset of A? Are all the members of C in A? All right, is the 1 of C in A? Yes. Is the 2 of C in A? No. Okay, that's it. We don't even have to go any further. Are all the numbers of C in A? No, so that's not true. So is subset commutative? No, it is not commutative. Subset is not commutative. All right, some sets. You'll do a lot more with sets next year in geometry, and we'll bring it up occasionally this year. All right, capital C. Last thing we need to talk about are the number sets. So C, number sets. Number sets. All right, again, we need now our classification system. We need our classification system, our filing system. Now, I'm going to start backwards just by way of illustration, then we'll explain each of these sets. But if you think about the file folders, the largest file, I'm going to do this off to the right, would be the real numbers. That's our number system, the real numbers. And the real numbers has two files in it, the rational numbers and the irrational. Now the irrational, that's it. That's once you get to the folder with irrational numbers, there's irrational numbers in it and nothing else. However, the rational numbers has in it another folder, and you can further take that down then to the integers. and take the integers down to the whole numbers and the whole numbers down to the natural numbers. Okay, and we talked about this last year, so this should be review, and hopefully it is. Okay, so usually we start with the natural numbers, and so that's what we're going to do here. Number one, natural numbers. Natural numbers. Okay, the symbol technically is a double-lined N. Sometimes you don't always have that font, but that's the way it should be. That's not the prettiest one, but that's the idea. That's the concept. Okay, what are the natural numbers? Brace. Natural numbers start at 1. The next one would be 2. The next member would be 3. And at this point, I can go dot, dot, dot. Now, the natural numbers is an infinite set. It goes on forever. And it's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. Keep counting forever. Okay? That's the set of the natural numbers. Now, every natural number, if you look over to the right, every natural number is also part of the whole numbers, but the whole numbers has a little bit more. So number 2, the whole numbers. Now we got to have a fancy W, and usually it's double lines on this orientation. That's the ugliest W I've ever written, but that's supposed to be a W. All right, and then brace. Now here's the whole numbers are just like the natural numbers, only they have one more element in them. They have the 0 in them. So 0, 1, 2, 3, dot, dot, dot. So you say it's real similar. Oh yeah, it's just got one extra member, and that's the 0. See, the natural numbers is the smallest group. Then the whole numbers is a little bit bigger. The integers are bigger yet. Rational numbers bigger yet, and the real numbers, bigger yet. And that's the way it goes. All right, number 3. Next comes the integers. And the symbol for the integers is a Z. Why is it a Z? I do not know. No, it's, I guess, Latin. So integers is Z. Now, with the integers, we get all the negative numbers. So, and it goes on for infinity in the negative direction. So we got to start with 3 dots. And I'm just going to go -1, 0, comma, 1, dot, dot, dot. So is -10 an integer? Yeah, because the 3 dots say it goes on forever in the negative direction. Is 47 an integer? Yeah, it goes on forever in the positive direction as well. Again, this is an infinite set. And notice how we're getting bigger. So now we added all the negative numbers. So if we were thinking back to subset, here's what we can say. We can say the natural numbers are a subset of the whole numbers. The natural numbers are a subset of the whole numbers. But you know what? We could also say the whole numbers are a subset of the integers. So let me pause. Are all the natural numbers in the whole numbers? Yes. Are all the whole numbers in the integers? Yes. They're subsets. Okay. They are subsets. What's next? Number 4, rational numbers. Rational numbers, and rational numbers is a Q, and usually we put the double lines on both sides, a Q. And look, I can show you a fancy thing, the set of all ABs such that A is an element of Z, B is an element of Z, and B does not equal 0. All right, that's real fancy. That's called set builder notation. Don't get caught up in it. But it goes like this. Brace A divided by B, a vertical line, which represents such that. And then we list A is a member of Z, an integer. B is a member of Z. It's also an integer. So the A is an integer. The B is an integer. And B cannot equal 0. So B does not equal 0, close the brace. All right, what is all that saying? Here's what they're saying, fractions. Fractions. That's what the rational numbers are. Anything that can be listed as a fraction, anything that can be listed as a fraction are the rational numbers. Okay, anything that can be listed as a fraction. Last one, number 5, irrational numbers. Irrational numbers. By the way, if you want to be famous, try to find an irrational number that can be made a fraction. The answer is it cannot. All right, the irrational numbers can be listed like this. Take the Q and give it an apostrophe. Now, what that means is Q prime. So in words, this would be Q prime. What is Q prime? That's an implied symbol there and there. Any number that is not a rational number. Anything that is not a rational number. Anything that is not a rational number. Okay, you say, well, what is that? I don't know what that is. Let me give you a couple examples. A lot of roots are square root of 2. So if you were to take your calculator out and you were to take the square root of 2 and you punch it into your calculator to find the value. So I'm taking my calculator out right now. I hit the number 2 and I hit my square root button. It says 1.4142135562, etc. Here's the point. I cannot find an integer for a numerator divided by an integer for a denominator to give me this exact value. I can get close. I can't get that exact value. By the way, if you want to be famous, try to find an integer on the top divided by an integer on the bottom that gives you exactly the value of the square root of 2. It doesn't exist. So if it can't be a fraction with an integer on the top and an integer on the bottom, we call it an irrational number. And again, it's a lot of the roots, square root of 2, square root of 3, square root of 5. There's a lot of it. Now, not the square root of 4, right? Because what's the square root of 4 equal to? 2. All right, don't be caught up there. Square root of 4 is a what? It's a natural number. It's 2, right? Pi, even E, you'll learn what E is later on down the road. 2.718281828. But anyhow, don't worry about that. All right, how do you recognize irrational numbers? These are, I'm going to do this in red, these are non-repeating, non-terminating decimals. Non-repeating, non-terminating decimals. So for example, 0.66666 repeater. That's not an irrational number, right? What's 0.66666? It's 2/3. That's a fraction. That's a rational. Okay? So a repeater, no. So it's a non-repeating, non-terminating. It's got to go on forever, but it doesn't repeat. That's an irrational number, and that's all these radicals and pi and e, etc. So last thing, and that would be a Venn diagram of this whole system. A Venn diagram of this whole system, and it would look something like this. And let me make that a little smaller for you. Okay, so the real numbers is what this is, and you can see the left side of the left rectangle is the rational numbers, the right rectangle is the irrational. So let me help you out a little. We'll put a few things in. So over here on the right, again, you can pause this. Square root of 2, right, is an irrational number. Where would I put the number 3? Well, 3 would go all the way into the most specific set. 3 is a natural number. It's going to go there. If I had a 0, where would I stick a 0? Well, a 0 rational number? Yes. Is it an integer? Yes. Is it a whole number? Yes. Is it a natural number? No. So I would put the 0 there, right? That's how this works. What would be the integers? Okay, I would stick like a -5 would be in the integers. What would be in the rationals? Something like a half, right? It could be in this form, right? 0.75. Isn't that 3/4, right? etc., etc. We'll have some homework over this tomorrow in class. All right, that's it. We flipped the classroom. I hope you enjoyed the lesson, and we'll see you in class tomorrow, and I'll help you in class to try to understand all of this and work some homework over it. You all have a great night.